So today's lecture is about, it's not about intermolecular forces. We're kind of moving past that, but I just wanted to review them. One more thing about them. Intermolecular forces tend to explain why one substance has a higher boiling point or melting point than another substance. They will explain why one substance is at a liquid at room temperature, but another is at a gas at the same temperature. So that would be examples of that might be something like, oxygen is a gas at room temperature, but like water is a liquid at room temperature. Why a gas would behave non-ideally. And last year during honors chemistry, we talked about the ideal gas law. Remember that? So we can use intermolecular forces to explain why gases don't follow that rule. Why one gas would have an incredibly high vapor pressure and another gas would have a low vapor pressure at the same temperature has to do with intermolecular forces. Why one liquid would have higher viscosity and another would have lower viscosity at the same temperature, and why one substance will or will not dissolve in another substance. All of those things are based off of intermolecular forces. So moving along. Phase changes in intermolecular forces. We know that when a solid goes to a liquid, it freezes, or solid goes to a liquid, it melts. When a liquid goes to a gas, it vaporizes. When a gas goes to a liquid, it condenses. And when a liquid goes to a solid, it freezes. We also have the really, really super big boy and big girl terms that when a solid goes directly to a gas, we call that sublimation. And when a gas goes directly to a solid, we call that deposition. Do you need to know sublimation and deposition and vaporization and melting and freezing and condensing? Sublimation and deposition, probably not, but you should know that they exist. Most common example of sublimation would be what now? Dry ice. Deposition, we can force that to happen. It does happen, but a lot of times people will see that as not as frost, but like that's a way to sort of view it. Like if we have water vapor, like really, really foggy nights, and we wake up with frozen solid. It was snowing this morning. Like you love snow. Okay. All right. So say that 3 weeks into winter. Same. All right. The link between phase change and intermolecular force has to do with the fact that there is energy required to separate the force of attraction that holds molecules in these positions. And because there's no new substance formed, we are just simply separating them. That energy is put in to break those attractions. I don't want to call them forces or bonds. I want to call them attractions. And you should also be in the habit of calling the way that molecules are stuck together, you call them attractions, because if you call them forces and bonds on the AP exam, they will mark it wrong. The reverse process is also true, so that if we want to take two objects and stick them back together, like in this case, we have two water molecules, and we want to stick our water molecules that appear to be gaseous because they're not attracted to one another at this point, or they're not near enough to be attracted, then they're gas particles. And so if we take those gas particles and we make them become liquid water particles, like over here, there is energy that's released. So we add energy to break forces of attraction, and we release energy to create forces of attraction. And then the next slide that we're going to talk about, you should be familiar with this guy. We spent a lot of time with this last year when we were doing like phase heating curve and phase calculations and those kinds of fun things. And so we're going to do some more of that this year. Yeah, there's some, I think this homework, I think you have a couple of this homework. So remember, as we add heat to a system, so as temperature increases, we are looking at the correlation between energy and essentially the amount of, as the temperature is increasing, we're essentially looking at the amount of energy in the system. So I increase the temperature, the energy increases, and we can go from solid ice to ice and water as it's melting, and then we can go from liquid water to vaporization, and then we can go to water vapor. So it's all about an increase in energy, and I have a feeling that bell's going to ring in a second. So while that's loading, What?
No,
Oh,
he just
okay.
has a really good sense of time.
So during phase changes, things that we need to remember are the temperature remains constant. So here would be a phase change. So from D to E would be a phase change, and from B to C would be a phase change. The temperature stays the same because we're trying to get all of the substance in question. In this case would be water. All of the water has to be vaporized in order for the temperature to go up. We're adding energy until we break all of those forces of attraction. During temperature changes, so like from here to here is a temperature change, the energy is being added to increase or decrease the kinetic energy of the molecules of the system. And once we get enough kinetic energy, then we will see things like bubbles start to form. So water would boil, for example. But they always say things like you should never watch a hot pot if you wanted to make it boil faster. You ever hear that?
Yeah.
Like never watch a hot pot. That doesn't make any sense because it's going to boil when it's darn well ready to boil, which essentially means that when the water has enough kinetic energy, then it will boil. So you can watch it. You're just wasting your time is essentially what's happening there. So
Like a microwave saying like that?
a microwave saying,
Yeah. A washed microwave won't boil your water. No, not with a... I finished myself.
I'm happy that you're satiated now. Then we have these triple point, these phase diagrams. Oh, this is going to be part of your homework this weekend. We have these phase diagrams. This one is for water, obviously, because it says so, and this one is for carbon dioxide. And we talked about these last year where we identified where the triple point and the critical point were. The triple point of a substance, remember, that is defined as the temperature and pressure at which all three phases, the solid, the gas, and the liquids, are existing at thermodynamic equilibrium. We haven't talked about thermodynamic equilibrium yet. I don't think that we really covered it at all last year either. But essentially what that means is that they are at equilibrium, which means that the energy required to make a solid, liquid, and gas are all exactly the same at that particular point in time. That's the triple point. Critical point is the point on a phase diagram in which both the liquid and the gas phases of a substance have the same density, and therefore we can't tell them apart. So a gas and a liquid would have the same density, and they behave the same, but they're two different things. So those are your triple point, your critical point. On the AP exam, are you going to see a phase diagram like this and ask to identify what's going on? Maybe. Will you need to know about triple points and critical points? Probably. So this is just a review from last year. And then following that up, at some point you will be asked to look at different compounds and be able to identify which compounds have the higher melting point or boiling point just simply by looking at them. And you have to use your knowledge of intermolecular forces to do so. So they may, definitely for this test, but they may be asking you questions. They probably wouldn't ask you a question like, here's four molecules, which one has the highest melting point? They might infer that knowledge. So they might say, if this particular molecule has a melting point of, I don't know, like 75 degrees Celsius, they might ask you to infer why it has a lower melting point than another substance. And you would have to be able to come up with what they're really looking for you leading down the path to talk about these specific intermolecular forces. So again, compounds with stronger intermolecular forces are more strongly attracted and will require more energy to separate the molecules from each other. So the greater the boiling point and melting point for that matter, the stronger the intermolecular force. That is a pretty solid rule of thumb. So if I'm looking at water, which is liquid at room temperature, but its boiling point is 100 degrees Celsius, and this is sulfur, it's hydrogen sulfide. It's actually also known as hydrosulfuric acid. Its boiling point is negative 60 degrees Celsius, and it's a gas at room temperature. So the question that you have to be able to understand is why. So because oxygen is significantly more electronegative than sulfur or any other element in that particular group, remember the group is the up and down on the periodic table. So it's your They're not going to see this table, this group right here. Okay. The periodic table that you need, but I refuse to give you. And because it's very polar and because water is a very polar molecule, even though sulfur is also, the sulfur is also polar as well. Oxygen participates in hydrogen bonding, sulfur does not. And because hydrogen bonds are more difficult to break than dipole-dipole interactions, then we would say that water requires more energy to separate than hydrogen sulfide. Does that make sense? Make sense? Yes, because hydrogen bonding.
Yeah.
What he said. This is not something you have to memorize. This is not something that you have to know anything about other than the fact that what this is essentially trying to tell you is that there is a trend based on the a molecule size. And as a result of the molecule size, there's a distinct trend in terms of boiling point. So according to the trend, so in the first row, we have methane, and then we have ethane and propane and butane and hexane and heptane and octane and nonane and decane. All of those are identifying a very specific number of carbons. So like decane has 10 carbons and methane has 1 carbon in its chain. So as we increase the number of carbons, the molecule size gets larger. And because the molecule size gets larger, there's an increase in surface area. And because the surface area is bigger, the van der Waals forces, specifically London dispersion forces, and I'm not too worried about van der Waals, but London dispersion forces are increasing as well. So because there's more point of attraction or more point of surface area for these molecules to touch each other and be attracted to one another, the more difficult it is to separate them when it comes time to boil them. So methane boils at negative 161 degrees Celsius, which is why it's a gas at room temperature. And decane, which is a pretty large molecule, boils at 174 degrees Celsius, so almost a full 100 degrees greater. Octane is the stuff that we put in our gasoline so that we can power cars. And octane has a pretty high boiling point of 125 degrees Celsius. So that's one of the reasons why we use octane instead of like ethane to power our cars. And yet ethane still is in our gasoline because corn is cheaper to make than than oil. So what now?
I like how they were creative with like the first 4 names, and then they were like, we'll just put the prefix on.
And that's an organic chemistry thing. I'm not 100% sure why they didn't call it monane and diane and triane, but the one that's the butane. It's not butane. Okay, so anyway, you're gonna learn all about this stuff over winter break.
Oh yay!
Good, clean family fun.
Yeah.
Sit around. Well, you can still do organic chemistry in Mexico. That's all I'm saying. You can still do organic chemistry in Arizona.
Do we have to?
There's going to be a test when you get back. Yeah. All right. So
strongly recommended.
How long is like the assignment over?
I try to give it to you about a week ahead of time so you can start working on it. But
Last year I had everyone complaining about it.
yeah, because they literally waited until the Sunday before we came back, and they were like, and I told them, I said, listen, if you dedicate like 20 minutes a day to this. Just like 20 minutes a day, like literally one night of homework a day, this won't seem that bad. And yet like all of the people except for like 3 people were like, you know what we're going to do? We're going to wait for Sunday night before we come back from break. We're going to wait until like 8 o'clock on Sunday night and start pounding this sucker out. And then of course they were really upset about it. Well, no kidding. Oh wait, Blair came complaining to school any day?
No, I studied the Sunday before. Which was like, oh my god, I waited.
Anywho.
Wait, how long do you think it would take us? Are you still recording?
Yes.
Yeah, this is all on tape. How long?
I don't think I said anything that's not true.
Well, yeah. How long do you think it would take us to, like, how much work is it? Is it shorter than a summer assignment?
Yes.
Okay. I feel like How much shorter is the percent?
I don't know. All right, so compare the boiling points of NH3, which is ammonia, and AS. I mean, it's not that I'm not answering. I just don't know the answer to that question off the top of my head. Okay, so NH3, which is ammonia, and AS3, which is arsenic and trihydride. Using an AP level explanation, and what I mean by that is a statement rather than just one word. Describe which compound will have a higher boiling point. Well, they're both trigonal pyramidal, right? But NH3 is going to have the higher boiling point. Now, here's the part so if this was an AP question, this on your exam, this would be 2 points.
That's all?
Yep. You would get 1 point for correctly identifying and 1 point for your explanation.
What if you explain it?
Good question. If you correctly identify and you explain it wrong, they'll just give you 1 point for correctly identifying. If you incorrectly identify and explain it right, you don't get any points. So it's 50-50 guess, and you just write down words. You could get 0, 1, or 2, depending on whether you guessed right or not. So anyway, here's the reason behind this. Nitrogen or ammonia is participating in hydrogen bonding, whereas ASH3 does not. And as you go down the nitrogen group, boiling point would tend to decrease. So boiling point would tend to decrease. Why would boiling point tend to decrease as you go down the group? So like we have like the nitrogen and the phosphorus and the arsenic and the antimony and the bismuth and the UUP, right? So what? Because it's fun to say, bismuth.
No, it's in Pepto-Bismol. Yeah.
It is in Pepto-Bismol.
Pink, but it's pretty.
Bismuth is not pink. Pepto-Bismol is pink. Bismuth is a white powder.
Yeah. No, but it's pretty. I'm talking about it's millennial pink, that's why.
I know. Anyway, so boiling point tends to decrease as you go down a group. Anybody want to try to explain that? Hi, how's it going?
I don't know. First off, it wouldn't be hydrogen bonding anymore as you go down.
True. What else? So like compare, like I'm telling you that bismuth trihydride, this guy right down here, would have a lower boiling point than arsenic trihydride.
It's because as you go down a group, the attractive force of the no, because that would be intermolecular forces.
Okay,
It would just have less attraction.
You're on the right track. You want to take in, JR?
It's because like it's less electronegative.
That's part of it. So there's less electronegativity, right? And the electronegativity, remember, that's the pulling of electrons in the bond toward that atom. But remember, we're really trying to talk about why a larger molecule would have a lower boiling point as you go down. And one of those things, because we are talking about as you go, so this is hydrogen bonding. And this is, what type of bonding is this? Would this be if I had two arsenics bonded together? Potentially dipole-dipole?
At the least it would be London.
Right. So this would be dipole-dipole because it'd be pulling towards the arsenic. So then as you go down, it's going to be dipole-dipole-dipole-dipole-dipole-dipole, right? But they're becoming bigger molecules. As a result of them becoming bigger molecules, there's a possibility that there might be some repulsion. Okay. Does that make sense?
Yeah.
Moving on. We're doing on time. Oh, we're doing fantastic. Look at that. We're almost done. Dunzo. All right. For today. Like
But
totes.
we have 2 days, so at
Right.
least, hey, be happy
Well,
to
you
give
know I'm gonna
this.
wait till Sunday night at
Be
8.
happy
Right,
to give
right.
this to us on like a Tuesday.
Anywho, compare the boiling points of butane with isobutane. Here's the thing. These guys, this guy here, butane, and this guy here, isobutane, are the exact same. They're the exact same chemical formula, they're exact same chemical formula. They're just different structures. So these are isomers of one another. So why would something like butane, CH3, CH2, CH2, CH3 versus isobutane, which when you learn about the organic chemistry, you're going to say that you're going to find out that it is a trimethyl methane, which is what it actually is. Yeah, it's going to be all kinds of good, clean family fun. But so the issue is that the boiling point, which one would have a higher boiling point? And the actual answer that we're looking for here is butane itself. So this guy is going to have a higher boiling point. The London dispersion forces are greatest among the molecules of butane because the molecules of isobutane, because butane has a linear structure, so it appears to actually be a straight line. And as a result of it having a linear structure, they can stack on top of each other and be closely attracted to each other better than this mess right here. So like if I was to draw another one of these, it would look something like this. I lied. It would look something like this.
Will we be required to know that linear structures are more attractive than?
This is what I'm trying to show you. Okay. So do you see how I stack these on top of each other, like literally like stacking pieces of paper on top of each other? Okay. So this fits together a lot nicer than if I tried to stack another molecule here. Okay. And as a result of it fitting a lot nicer, the longer and straighter the molecule, the more places it will have to attach in terms of attraction. Whereas here, because it's this molecule, you have to remember that it's like in three-dimensional space, but like it's kind of a flat-ish molecule. Well, not a flat-ish molecule, but it's has less surface area than the straight linear one. Okay. And actually what I'm going to do right now is I'm going to hang on. Let's see if I can pause this. Okay, so.
Wow, Mr. B, you finished that so quickly. You're just.
Oh, I didn't. I screwed this up still. All right. So here we have. Here we have.
This is proof that Mr. B can control time.
All right. So here is butane. Okay, and here is isobutane. Okay. So the difference is that if I had a couple of these, I could stack them together in a lot neater of a package. So attraction like that compared to a couple of these. So if I tried to stick this, and right now the band kids are going, I can't even see what you're doing.
That's for you, Neil. We can't
Oh.
see what you're doing either.
So if I have two of the same, right, they're going to stick together or they're going to find forces of attraction. They're going to be slightly off. And as a result of that, there's going to be a little bit of, they fit together a little bit easier than if I tried to do this.
Arnie.
That's the appropriate time to do that.
Well, you're not saying anything. I wonder how much they're struggling to do the homework.
Okay, so like this conglomeration right here, okay, it doesn't have as much surface area for it to stick together. Does that make sense?
Yeah.
So the flatter the molecule, the more likely, the better it is to stick together in terms of forces of attraction. And as a result of that, the temporary dipoles, the induced temporary dipoles will form faster. So, and they'll be stronger than something that's a little bit more of a mess. Does that make sense? So the higher boiling point is the one with the straighter parent chain when it comes to intermolecular forces. Any questions about that? We
How do
good?
we even know that
We're
isomers
gonna make an
exist?
AP Chem shirt this year.
Yeah, AP Chem shirt. I'll design it.
I think it should have. I think it should have the picture of you on your website on it.
Of what?
The picture of you on your website.
I hate you.
Actually, me and Lauren made one. She dropped it. Izzy, do you really want it to be found on the internet?
All right. So one last thing. You guys want to say hello to the
Hi,
people?
band kids. Welcome back. We're getting so much work done without you guys here.
Okay. All right. We're done now.
Bye. Bye, friends. See you on Monday.